right, I think we're almost ready to go. Wait. What happened to the rock and roll? Well, I decided to go with a John Williams tribute concert today, which is why you hear the strange voices, because the guy has to come on and introduce the next song. The problem is the guy doing the introductions, because this is a concert in Germany, he's speaking German. So, but John Williams, fantastic composer. Like all of the major famous movie themes you've heard of, most of them have been composed by John Williams. Harry Potter, Superman, Jaws, Indiana Jones, like, okay, big film franchises. John Williams made the music. Star Wars, yep. All right, let's see. I still need to get in. Let's see. We've got Caitlin, Emily Z, and Daniela. Let's see, is that everyone? Oh, Ruby, Brian, Brianna, and Naomi. Do I not have Brian, Brianna, or Naomi? Do not. Okay. Let's start there. All right. Well, with that musical introduction out of the way, good morning, everybody. Hello, how are you doing? It is time today to take a look at our next type of sequence and or series. Okay? We're, of course, working on both of them at the same time. So we did the arithmetic sequence, or arithmetic series, and those were linear relationships. Now we go to the geometric series, which is a quadratic relationship, because a geometric series is generated from a common ratio. Okay? We are consistently multiplying. Instead of a common difference, that is to say you add each time, and so between the two numbers there's a difference. Now we are multiplying again and again, so between the two is a, well, I guess you'd call it a quotient, right? But since that quotient is consistent, more particularly, we're going to call it the common ratio, represented as two numbers divided. So like we did with the arithmetic, I want to quickly run through and build up the derivation of that general formula, just so you can kind of get an idea of how this comes to be. If I start with the, I wanted to say reciprocal, that's not the term. It's not the general rule, it's the, now I've lost the word. My apologies, right? The recursive, right? Where to get the next term, you multiply the old term, right? A sub n depends on a sub n minus 1 times r. So from this rule, I can generate the sequence, right? No problem. I can keep going and going and going. But I can only go one at a time. If I want to jump ahead and say, what's the 100th one? I got to first get the first 99. That's annoying. So let's take a look at what happens when we start generating these, see if we can come up with a general formula. The first one I'm just going to call a sub 1. That's going to have to be our starting point. It'll be whatever we start with. And then the second one will, of course, be r times a sub 1, right? Take that first one, multiply by r. Then the third one is going to be take, well, the one before that and multiply by r. But I know the one before that. That was r times a sub 1, right? So isn't this r squared times a sub 1? Okay. Same with a to the fourth is now going to be r to the third power times a sub 1. So this is the pattern. So just like we saw with the arithmetic, it's always that first term plus so many of the constant difference. Now it's the first term times so many of the common ratio we're calling r. So in general, a sub n is going to be the first term times that common ratio. How many times do you want to multiply by the common ratio? You want to multiply by n minus 1 times, right? This is just so that when you put a 1 in for n, you don't multiply by r at all. You get back to a sub 1, right? 1 minus 1 is 0. Anything to the 0 power is just times 1. So we effectively get no times of r, right? That's probably the biggest catch on there, is to watch out that the nth term uses the n minus 1th power. Okay, make sure you're 1 off from that. And this is, again, this is just so that our starting point, so our 1s work out to be the first term. And same with the arithmetic sequence. Be very careful with a negative r. That's going to change the sign of things, right? If I'm multiplying by a negative, but I'm multiplying by a negative now, and I'm multiplying by a negative, notice r is being raised to a power. So the full sequence, your sign is actually going to flip. As I multiply by a negative, and then I multiply by another negative, well, now I've got 2 negatives, the whole thing is positive. Then another negative, whole thing is negative. Then another negative, whole thing is positive. So it's going to alternate signs there with that negative r. All right, something to watch out for. And in fact, I don't remember if the book section summarized this. If not, definitely add this table to your notes. If they did, we'll go through it again. What types of r, specifically signs and values of r, and what happens to that resulting sequence or series? Okay. When you have just regular old large positive number r, pick, I don't know, 5, 12, 7,000, whatever it is, right? Any r that's more than 1. Okay? It's positive, so the whole sequence is positive. Okay? The series, which would be the sum, will also be positive, adding up a bunch of positive numbers. Okay? And the numbers get bigger and bigger and bigger, right? I multiply by 5, and then multiply by 5 again, and then multiply by 5 again. It's larger and larger and larger. And so my, both of them, you know what, let me shorthand this. We're talking about the sequence and the series. So they will both stay positive, and they will approach infinity, right? The sequence is going to approach infinity because the numbers themselves are getting larger and larger and larger. And the series, right? The series is the sum of the items in the sequence. That's going to approach infinity as well, because now I'm adding more and more and more together. In fact, it's going to take off even faster, right? Does that make sense? Anytime r is greater than 1. Now, if r is between 0 and 1, so that is to say it's a positive fraction, okay? I am multiplying by, best example, 1/2. If you want to conceptualize this, pick the easy one, 1/2. If I keep multiplying by a half, times a half, times a half, times a half, right? What happens? Well, my numbers themselves are going to get smaller, right? We're still dealing with positive results here. Okay. The sequence, though, is going to approach 0. So my numbers get smaller and smaller, right? Times a half. We'll say just 1. 1 times a half, times another half is a fourth, an eighth, a 16th, a 32nd, right? You get smaller and smaller fractions as you go. You got to asymptote at 0. What about the series? What do you think the sum of those things is going to do? If r is a small fraction. If you start adding up 1/2 plus 1/4 plus 1/8 plus 1/16, it depends. So I'm going to write k for constant. It's going to converge to some constant, usually. I can't say for certain which it's not like it's always going to be 1. Depends on the particular setup that you have, right? But it is going to converge to a single number, right? It won't get to 0 because we're adding entire numbers here, right? It definitely starts larger than 0. I'm adding more to it. But it's not going to take off to infinity because the fractions that I'm adding are smaller and smaller. So usually the series will approach some constant. So you'll have like a final answer. Like, what is the sum of this crazy series? And you're like, but I'm adding an infinite amount of numbers. Yeah, but those numbers like approach minuscule fractions that barely affect anything at all. So eventually the whole thing will just come out to be 5. Okay? Now, for these guys, this is the same scenarios, except now r is negative. So if r is less than 0, but still greater than -1, that is to say a negative fraction, okay, we're going to have alternating positive, negative entries, right, in our sequence. So the sequence will still sort of approach 0, but in a wavy sort of fashion, right? Let's say the absolute value of the sequence still approaches 0. The series does wonky stuff at this point, okay? And that's going to be true no matter what. When r is negative, it starts to get a little weird. Okay? And that we could go constant, we could go infinity, we could go 0, right? 0 could be one of our constants. So we've got a large variety of possibilities here. And then we'll note down if r is not greater than 1. Wait a minute. I've got this backwards. This should be r less than -1. There we go. Right? If r itself is -5, multiply by -5 times -5 times -5. Again, we've got that alternating positive negative sign. The sequence values, right? The absolute value will approach infinity, but of course they're jumping back and forth. Plus this minus that. Plus 1 million minus 2 million, right? Plus 3 million minus 4 million, okay? So what happens when you add all of those up? It depends. Can't give you a good general rule there. Okay. Any questions then in general on these guys? No? Okay, let's do a few examples here together, and then I will leave you to your quizzes for today. So, first up we have, we'll start with blue. Find a sub 6, that is the 6th entry in our sequence, when a sub 1 is 8 and r equals -1/4. So our common ratio, okay, is negative, and it's a fraction. So look what that does. They're going to alternate signs here. Okay? It's going to get smaller and smaller because I'm multiplying by fractions. The absolute values will get smaller and smaller. 6th is that borderline case where we could go all 6 items from 1 up to 6. That wouldn't be too bad. But for the sake of example, let's go ahead and figure out the general formula, and then we'll just plug in 6 for n and hit straight to our answer. Okay? So this sequence, in general, any a sub n is going to be that first term, 8, times the ratio -1/4 to the power n minus 1. Okay. And so a sub 6 is going to be 8 times negative 1/4 to the 6 minus 1, that's 5, right? The fifth power. Okay, anybody happen to know what 1/4 to the fifth power is? 4 times 4 is 16, times 4 is 64. That seems like a lot. Yeah, let's just go for the calculator, right? Do I have, let's see, can regular calculator app pull off to the fifth power? Not now, I don't need to rate it. Where's my exponent button? There it is, okay. So we're gonna go 1/4, that is 0.25, right? To the fifth power? Wow. Look at that, teeny tiny. I know, it was supposed to be negative. But we know our rules for negatives to an exponent. If it's an odd power, which to the 5 is, then the result will be negative. So it's negative 0.00097, and that times 8, right, to get our sixth entry. If you're using your TI-84s, you can go ahead and press that math frac button. Let me see, I have the X. Let's see if we can do it on here with the calculator. So we can do it all in one entry. 8 times there, negative 1/4. You can do it as a fraction if you like. To the power 5. Enter. There we go. There's the same item, but now with our negative sign that we knew had to be there. And if we go math, 1.
Fun things to do near you. Yep. 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 There's a Groupon for that.
Thanks. Thanks for that. That's exactly what I needed. There's a Groupon for that. Okay. Negative 128th, if you like it in fraction form. All right. So the answer is, I like fractions, negative 128. I'm just going to leave it like that. Okay. Any questions on how to compute such a problem? Hope YouTube doesn't yell at me for that ad. All right, next up, how about sums? Find the sum from 1 to 8 of 2 times 3 to the I, right? So I is our index. This is like our nth term. So we're finding the first 8 terms. You guys see how to read and interpret this? This is find the sum. Here is our general rule. How many terms? Terms from 1 to 8. Okay. So we could list out all 8 of them, add them up, or the textbook did more of the derivation for you, but this is very similar to the arithmetic. So with the arithmetic, we were adding all of these terms that had a constant difference. There was that linear relationship, and so we could find basically the average and say, oh, well, the average term is this times how many we had. And so the sum formula is based on averages here. This is a little bit different since it's a multiplicative average. And there is such a thing. If you're familiar with the geometric mean, different from the arithmetic mean, the mean you're used to, add them all up, divide by how many, is the arithmetic mean. The geometric mean is when you multiply things up, right? Instead of add them up. And so this, if you're familiar with the geometric mean, this is a geometric mean, okay? Taking my starting position, I'm multiplying it by this power so many times, divided by one extra instance of that power to get my total sum. Okay? So it's similar. It's a related concept. Just want you to be able to identify that. It's still, how many times did I multiply them up? Well, on average, I multiplied them this many times, right? This is our middle result. So let's take that formula and apply it down there. So we take the first term times 1 minus r to the n over 1 minus r. So S sum of the first 8 terms equals our first term, 2, times 1 minus r to the n, that would be 3 to the 8th, right? Notice here the number that has the exponent, one that's on the index, that's our ratio. 2 is our starting value. If I was 0, right, with no extra terms, we would be left with 2. Right? So we know 2 has to be the first term. And then how many times am I multiplying by 3? Oh, you're multiplying up to 8 times. Right? So 3 must be our r, divided by 1 minus r. Right? So let's simplify this a little bit here. We've got 2 times 1 minus 3 to the 8th. Ooh, I don't know that one. But I know this is negative 2, right? 1 minus 3 is negative 2, which means these 2's can reduce with each other. That's handy. The negative sign is still there, but 3 to the 8th is definitely more than 1. Would you agree with that? Clearly it's going to be more than 1. So this will be a positive number in the end. It's just going to be 1 minus whatever 3 to the 8th is. That's a heck of a lot. Let's try the calculator again. Okay. 1 minus 3 to the 8th power. Negative 6,560. Except we're dividing that by negative, so that comes positive 6,560. Does everybody follow that? Did I lose anyone? No? Okay, and final example here. Find the sum of this guy. Okay, what do we got going on with this series here? Notice the numbers are getting smaller, right? We're dealing with a larger and larger denominator. Numerator stays the same. So I'm dealing with smaller and smaller fractions, right? In fact, we can kind of, let's rewrite this a little bit. 25 is 5 squared. Okay, we should recognize that one right away. 25 times 5 is 125. That means this is 5 cubed. And that kind of reveals to us a little bit more what's going on. What's the general term here? We can easily see first term is 4. And then that's being multiplied by 1/5 every time, right? To the n minus 1. So now let's use our summation formula on that, right? So we want to, wait, what's our n? This says the sum of the first 8 terms. This just keeps going out to infinity. Ooh, we need a different formula for this. What about an infinite? The sum, let me switch to a different color here, right? Check your notes. the sum of an infinite geometric series is going to be the first term divided by 1 minus r. That's it? That's easy. Yeah. That's a lot simpler, right? At least if it converges, right? If r is between -1 and 1, right? Again, if it's more than that, if you're trying to sum all the way out to infinity of a series whose entries themselves, whose terms themselves are growing up to infinity, then of course the sum is automatically infinity. You can just see that. Like, well, eventually I'm going to start adding 1 million plus 2 million plus 3 million, right? So, oh, this just grows insane, okay? This guy, they're getting smaller and smaller, so we can actually find a sum. It does converge to a single number, and we can find it like that. So this guy, this sum is going to be, our first entry is 4, divided by 1 minus, r is 1/5 here. Okay, 1 minus 1/5, well, 1 is actually 5/5, right? So 5/5 minus 1/5 is 4/5. And instead of dividing a fraction, I'm instead going to multiply by the reciprocal. And now look at that. The 4's reduce, and our answer is 5. That's it. In my opinion, infinite series are easier to deal with than finite series, right? This was a little more complicated involved. The formula itself is literally more complex. There's more things in it. This is actually really short and sweet. I like this one. There you go. Questions there? Okay, then we've got a 12-question quiz. So have your notes at the ready. Go to joinmyquiz.com. Enter the game code 262251. 262251 for some short, sweet practice. You will make use of all of these formulae as you go. Look at that, they all come at once. Okay. As always with our quizzes, retake code will be posted at the end of classes today. Oh. And if you finish early, go ahead and start on the exercises. Got 12 in, 15, need 3 more. Okay, those of you in, go ahead and get started. Shh, way too loud. Okay, 262251, still open. You can still join in and get going on your first run. All right, 83% off to a great start here. And we'll wrap up the YouTube.